Okay, it's probably time to start the session while people are arriving. I'm Richard Blundell, currently President of the Royal Economic Society. And before I introduce the Sargan lecture for this year, I thought we should say thanks to the organizers. That's Francesco and Chrissy and Pramila and Solomus. And there are many other supporters, so let's give them a round of applause. They're already through the worst bit, as it were, and we know now that it's a very, very successful conference, so thanks very much. It's my real pleasure to introduce Ariel Pakes, professor at Harvard, previously at Yale, Frisch Prize winner, and many other accolades. When I think of Ariel's work, I think of the creative force behind the new wave of empirical industrial organization work. This has revolutionized the IO literature over the last 2 decades, being precise about the nature of the game, precise about the nature of preferences and costs, and precise about the data. Ariel's work has been influential through his publications, but also through his many students. I notice he won the Best Graduate Student Advisor when he was at Yale, and there was a kind of prolific period with many students. So it's a pleasure to hand the floor over to Ariel Pakes for this year's Sargan lecture. Thank you.
First, thanks for inviting me, and thanks, Richard, for the introduction. What I want to talk about today is what I call interpretable reduced forms. And what I want to suggest is that for a reduced form to be useful, it has to have an interpretation. And I'm going to try and provide you at least one interpretation, which I think will be useful in microeconomic models. So let's see how this goes. Changing. Don't change on here. Somebody note page down, maybe. Yeah, OK. So I'm going to start it with the general setup of a decision problem, and then show you what a reduced form to this decision problem looks like. Okay? The setup is going to be that an agent chooses a D, a decision, among a finite set. So I'm going to focus today on discrete choice. So I could have done it continuous. The agent chooses, and the agent knows he has an information set, which is JI. And the agent has its own expectation operator, E. Okay? And it's going to use that. The agent's going to use that expectation operator to evaluate different decisions. Okay? There's a random outcome to the decision, which will vary with the decision, not all of which we observe. Okay? And the expectation of this random outcome, given D, given his choice, I'm going to call that VJD. So that's going to be the object of interest, okay? Which is what the agent expects the decision to bring to him, or the utility, or the profits, whatever it is. And then he will choose D to maximize among the set he can choose of his evaluations. Okay? So that's the setup. Page down doesn't seem to work anymore. There we go. OK, so my goal is not the behavioral model. Even in the end, my ultimate goal might be the behavioral model. But as an intermediate step, I want to characterize this valuation. Okay? And I'm going to provide a characterization and then show how to estimate it in some examples. Okay? So E is now going to be a different expectation operator. It's the expectation operator generated by the data generating process. So it's the actual thing that generates averages in your data. Okay? And what I'm going to claim we want as a characterization is the expectation of the evaluation function conditional on some x, some variables of interest. Okay? So that says, just writing that, that's a different expectation operator than the agent's expectation operator generally. Okay? Just writing that down, I get the valuation is the agent's expectation, the expectation of the agent's valuation plus an error. And by construction, the error is mean 0. Okay? So if I do GD as linear, I'm looking for a best linear predictor of the agent's valuation. And if I do actual regression functions or expected values, I'm looking for a minimum mean square error predictor of the agent's evaluations. So, you know, I think our ultimate goal in doing empirical work is to get the actual V function, okay, which is the behavioral function. It's what I've worked most of my career on, okay? But now I want to consider the reduced form, okay? And I'm going to argue that in many initial studies, we really want to start with GD, basically because a good model for V must rationalize what's ever in the reduced form for G. So there's relationships in the data, and if you're going to have a model which explains the valuations and the agent's decisions, you better be able to rationalize what's in the data. So you might want to start on hard problems with just a characterization of what's in the data. Okay, so that's what I'm going to try and do. So I'll give you some examples. Just 2 notes before we go on. This I already said, which is the expectation operator that we're actually going to try and measure, okay, doesn't necessarily have to equal the agent's expectation. So the agent's expectation need not equal the averages in the data. And indeed, the difference may well be of interest. It may well be of interest what the agent knew and what the agent didn't know, if he made errors, didn't make errors. We can talk about that, but in various cases, that's maybe of most interest. So that's one thing I want to point out. The second thing I want to point out is the reduced form disturbances on the other page. That is the new in GD plus new. They're by construction additively separable, okay, and orthogonal to the included variables. That's just by how I constructed the thing. Okay, so here's some examples of things that I would say are really begging for a reduced form. So almost all 2-period models are reduced forms. In IO, this started as entry models. Now there's buyer-seller networks, small number of agents with multilateral bargaining between the various agents. 2-sided markets. None of us, I think, believe that that's a structural model, that there was no one there the period before, and they were there the period after, and nothing happened thereafter, okay? So in some sense, we're trying to get a reduced form. I think well, I know a lot about the entry models and the buyer-seller network models, and they were very successful in providing frameworks for organizing data on important economic phenomena. So you would learn what had to be in a real behavioral model about entry by looking at the correlations in the data. Okay, and you would do this by organizing things in a 2-period model. Okay, it was a 2-period model. It was not an attempt to really mimic the world. Okay. Another case where this happens a lot are choice models where the agent is uncertain about the characteristics of the outcome from the choice. But the researcher doesn't want to specify the prior that the agent had, okay, or the conditioning set that the agent is conditioning on when he does his prior. Okay. So if you think about going to an outlet, say a supermarket, most people choose a supermarket. They don't know the distribution of prices over at the store in the supermarket. There are many prices, and there's actually a distribution of them. The agent had some prior on what was available at the supermarket, okay? But it's not the realizations, and if you put in the realizations, you're going not to get the agent's decision function, because there'll be an error, and the error will be correlated with the realization. There'll be an expectation that went into the function. There'll be an error, and you put in the realization, and the realization will be correlated with the error. Okay? So here, the reduced form we get is typically not the model we want. So it's a little bit different, but distinguishing between the two will be useful, and I'll come back to it. By the way, one of the examples will be this entry model. I will talk about this a little bit in more detail. Another example that I've worked on are choice models where the opinions of multiple agents go into the decision in an unknown way. Okay, so hospital choice in the United States, which is the one that I'm going to talk about today, a little bit at the very end, hopefully, if I get there, is a choice made jointly by the physician, the insurance company, and the patient. Okay? It's not really clear how that decision is made, and you might want a reduced form to figure out what it's a function of before starting to model it in more detail. Similar things can be said about household bargaining models. So those are the kind of problems I want to look at today and ask, is there a sense in which we can learn from the reduced form about them? Okay? So just 2 points that are going to end up being important. The reduced form of interest often explicitly incorporates some structural assumptions. So what happens in the entry world, in the entry models in IO, is there's a reduced form for the entry value or the continuation value once I enter, okay? But there's a structural form for the costs, for the sunk cost of entry, okay? And they put that together to form a model, okay? So it's going to work out that you want to be careful about the difference between the structural errors and the reduced form errors. They have different properties. So that's one thing that I want to point out. The second thing I want to point out is, in many of these cases, we want to allow for an unobservable component of what we condition on, okay? And an unobservable component with a particular structure. Let me give you the two examples that are most dear to my heart. So in two-period entry models, the reason this literature started is people wanted to characterize what determined the number of firms in a market and what determined the profitabilities in a market in just a rough way, okay? And what happened is one of the variables on the right-hand side was invariably the number of firms in the market. So the profits of my entry decision would depend on the number of firms in the market. And what would happen is you would invariably get a positive coefficient on that variable, which didn't make any sense from an IO perspective. The more competition, the less the profit should be, okay? And the reason was very clear that there were markets that were more profitable than other markets in unobserved ways, and more profitable markets induced more entry, okay? So the whole IO literature on entry started out by worrying about this problem and making the N endogenous, the number of firms in the market endogenous. That was the reason. Similarly, when you analyze price effects in demand models, you might want to worry about unobserved characteristics. So that's where BLP started. Also, this hospital choice problem. It's going to end up being important to condition on hospital quality interacted with diagnosis. When your diagnosis is severe, you really want to go to a good hospital, okay? So you should remember those two things. Those are two things I've got to keep track of. Okay. So most of this lecture is going to be on examples, which show how to obtain estimates of the reduced form, okay? And it's going to work out that to obtain estimates of the reduced form, I'm going to have to pay attention to how I construct the reduced form, which should not be surprising. So any reduced form won't do. But before I go there, I want a quick note on the relationship between my interpretable reduced form, or our interpretable reduced form, and behavioral models, okay? So I'm going to define something called weak rationality, okay? And we'll just say that an agent is weakly rational with respect to Z if the agent's expectation operator equals GDZ. Now remember, GDZ is just what comes out of the data, okay? So if the agent is weakly rational, he doesn't make consistent errors. He can make an error, but on average, he doesn't err, okay? So now, just given this, okay, there's going to be two cases we're going to have to consider. Okay, one is where Z is in the agent's information set. We often know that. Okay, if Z is in the agent's information set and the agent is weakly rational, the reduced form gives us the conditional mean of the agent's evaluations. Okay, because the conditional mean of the agent's evaluation is also the conditional mean of the data generating process. Okay. The natural question is, can we test weak rationality and characterize deviations from it? So I would argue that to do so without strong auxiliary assumptions, you're going to need outcomes as well as decisions. Okay? So in IO, we often do that. We often do have outcomes. We have profits, firm value, or tax revenue, public finance sometimes. But it's going to be hard to do when the object we're maximizing is utils. We don't see utils. Okay? But I want to push this a little bit and ask the question, if we do observe outcomes, like IO case typically, at least up to an error, I want to show that the tests actually become pretty straightforward, the test of weak rationality. Because you would just base them on whatever you can estimate, and I'm going to show you how to estimate this, of this GDZ, which is the expectation of the data generating process of the agent's evaluation, against the actual expectation of V. Okay? You actually see some realizations. I can regress it on Z, and I can compare the two things. Okay? So just two things. This test, when you do have this test available, it doesn't require us to specify the agent's information set, and it doesn't require us to specify the agent's priors, how he forms its expectations. Okay? So it's a test of weak rationality that's it's in some sense a lot easier to believe in than more structural tests of rationality, of strongly rational expectation model. And the second thing is, by comparing the two possible expectations, now we actually have a variable. We can see where the agent errs. And seeing where the agent errs might help us figure out what the agent's expectation operator is and build an appropriate model. Of course, again, to engage in such tests, I need appropriate estimates for GDZ, which is our interpretable reduced form, which I'm going to go to. Because that's one case. That's when Z is observed. Say Z isn't a member of the information set. So I'm going to condition on something the agent didn't know when the agent made its decision. Okay, then even if the agent is weakly rational, there's no reason to believe that what I get from the data generating process is the agent's expectation of the valuation. Because I'm conditioning on something he didn't know when I made the decision. So you would think this doesn't happen, but I'm going to argue that it happens a lot, much too much, in applied I/O and applied, actually, microdata analysis. So here's two examples where it happens. Say you have a structural model for V, but no model for the distribution of Z, of the random variable that's going to determine the outcome here, given Ji or the contents of Ji. So the example I'm going to go back to is this same example of you choose which outlet to go, but you don't know the prices of the outlet at the outlet when you choose. You have some prior of what's a cheaper store, what's not a cheaper store, what characteristics the store carries and what characteristics it doesn't carry. But you don't know it exactly. Again, if you use realizations of Z, you shouldn't expect to get an unbiased representation of the agent's evaluations. If he didn't know it, there's going to be an error, and the error is correlated with the right-hand side variables. Okay? Another model that looks like that is a model that's linear in Z star, which the agent knows, but the econometrician only knows Z, which is a polluted measure of Z star. So the typical errors in variable model. Okay? You're going to put in Z, the Z is going to be correlated with the error, and you're going to have trouble. So those things happen a lot. We just tend to assume them away when we work in discrete choice models. The thing to note about this is, in both these cases, any estimator which is linear in the resultant expectation or measurement error will average out the error. So the reason discrete choice does poorly in these cases, okay, it's because that the probability function that you're estimating is a nonlinear function of the errors. You're getting a p, you're integrating out, getting a probability of an event, and that's a nonlinear function of the errors. Okay? Moment inequality models aren't nonlinear functions of the error, they're linear functions of the errors. So when the outcome of the choice is subject to significant uncertainty, moment inequality should be thought of in lieu of discrete choice modeling. Okay? So I will get back to moment inequality as we go on, but thinking about exactly what you're doing and what the agent knew and what he didn't, and what you're trying to get for the reduced form function helps you through thinking how to estimate things. Okay? So now I'm going to turn to two examples where I try and estimate this reduced form function. One is a computational example, and one is an actual empirical example. So my goal here is to produce meaningful estimates of parameters that we might be interested in, and being explicit about the assumptions that go into the reduced form. Okay. So two-period entry models. These have actually been incredibly helpful in I/O. I mean, entry and exit are one of the basic equilibrating forces in industrial organization, just like price setting is one of the basic equilibrating forces. Okay, and they've been used to determine, to organize essentially cross-sectional data on the determinants of the number of firms or the number of firms of different types operating in markets. So if the market is larger, if there's different firms of different types, does it affect the profits of one particular type? And the relationship between the number of firms and markups or profits. And the framework is pretty simple. It says the following. There's a value for entry, which in my case would be V, this script JI, the agent's information set, if D equals E, if the agent enters. A distribution for sunk costs. And the behavioral assumption that D equals E if the value of entry is greater than the cost. Okay, so that's what's going on in these models. So I'm going to formulate my reduced form. Okay? I don't believe that the two-period model is right, but I want to know what this value of entry is correlated with. Okay? I want a framework for setting that up so that I can write down more detailed models. Okay? So I'm going to write it down just like we did before. I'm now going to call it G of E because the D is E, okay, plus V. And remember that this error now, by construction, is mean independent of X. And the agent will enter if GE plus nu, which is the value of entry, is greater than the cost of entry. Okay? So in these models, typically, they're going to assume full information. What they're doing is cross-sectional analysis. So full information means simply that no individual has an incentive to deviate. It's a Nash condition. Okay? And you would think maybe in the cross-section, that's the way to structure the data. Okay? In time series, you might think people make errors, but then you don't want in the cross-section because, you know, it would imply that people made errors and stayed there. They didn't adjust afterwards, okay? So that implies, by the way, that this C is going to be correlated with X because X is going to include the number of entrants, okay? So if, you know, if my C is very low and I enter, it will affect the other entrants' probability of entering because they know me, okay? At least in equilibrium, when we settle down to a rest point, they will know me, okay? So EC given X is not going to be 0, and its value varies independently of the entry value, okay? So there's going to be 2 errors in this model now because I formalized the reduced form part of it. There's this error and this error. This error was always there. Its expectation given X is not 0, and its value varies independently of the entry value. People get random draws on sunk costs, and they're independent of the entry value, okay? On the other hand, E nu X is 0, and its value just depends on the entry value. If you condition on the characteristics you want in the entry value, you're conditioning on nu, okay? If you see 2 people that at the same characteristics at the entry value, they have exactly the same nu, because that's the value we're trying to estimate, okay? Okay, again, I'm going to come back to this thing, but if GE is linear in X, okay, and that's what all these models start with, okay, I'm going to partition X into an observed and an unobserved component and let the unobserved component be correlated with X naught. So this is the issue of market effects, okay? So there are markets which are more profitable in unobserved ways, and I want to condition on that and look at the effect of the number of agents in, or the number of agents of different types in, okay, conditional on the market effect, okay? This was the original concern for endogeneity in entry models, okay, just as I said before. Whoa. Okay, so it's going to be a Monte Carlo, so this is just a standard Pakes model. We computed it with the Pakes-Boyer algorithm. The firms are going to differ by one of 2 locations. They're in different locations. And they're going to differ by a quality of product they invest to develop. So there's 2. In reality, I'm not going to condition on all these things, but in reality, in the model I've actually computed, firms have 2 characteristics. They have their location, and they have the quality of their product, which they're investing in continually, okay? Consumers are going to differ by their location, so they may be closer or smaller to the outlet, and by a sensitivity to price. So different consumers have different incomes, and that gives them different sensitivities to price, okay? Profits, there's going to be a Nash and prices assumption, which is conditional on these state variables that the firms have. It's going to deliver profits, okay? And then the dynamic model is Markov perfection, so that generates entry, exit, and investment policies, and those in turn generate a Markov process over the state of the market over time. So the state of the market is, again, each firm that's in its location and its quality of product. And this will evolve over time as a Markov process under these assumptions. Okay, so that's the real theory. And now I want to go back and try and estimate a reduced form without going through all the dynamics. Okay? Okay, so I now have a value of entry, okay, for an agent in location L when the market structure is sigma. So sigma is this list of where all the firms are at their productivities. And I'm going to say, look, this is what I want to estimate. I want to estimate a model where there's a dummy variable for a location, there's an effect of the number of firms in my location, and there's a effect of the number of firms in the other location. This is a typical kind of model that you would estimate in this thing. And you might want to condition on the market effect, okay? So now the error term in this projection is a function of sigma, which is the state of the market, okay? But sigma isn't observed to the agent, okay, because it isn't observed to the econometrician. So the econometrician is going to have to condition just on the S's that the agent observes, that he observes, that he conditions on the data, okay? Because for every one of these, okay, for every time I'm going to see particular things, and it's that S that I'm going to condition on, okay? The S is actually going to equal this X thing, and most of it. I'm having trouble with this guy. There we go, okay? And then I have to worry about the fact that there's the entry model also requires a C, and C's correlated S with X. So I've got to do the projection also of C onto X and get a residual, which is C star. So now the rule of entry will be, again, the parameters will now be changed, but the rule of entry will be agent J will enter if he's at location L, okay, when the market structure is S. The observed market structure is S. If VE LS minus CJ is greater than this reduced form value of entry, which is here, these 2 things, and CJLS, okay, where CJLS is now this compound of the various errors. Okay, so what you should notice is this VLS here, it doesn't change with states. It's defined as the error in the valuation. If I'm fixed at a given S, okay, it is that value, no matter how many times I hit this S. It's the same value. On the other hand, the CJLS, okay, is something which varies every time I hit this. Every agent gets a draw on the costs. Okay? And the reduced form parameters are going to be the ratios of reduced form. The parameters here, the theta instead of the beta, will be the ratio of will end up being in our model the ratio of beta to sunk cost. So all you can really tell in the reduced form is the ratio of the contribution of this to value to the cost of setting this thing up. Okay? So that's a setup. Okay, so here's the actual reduced form functions. Okay, so we actually computed the equilibrium. Okay, so I come back and I have actual reduced form functions. And these are the functions I'm going to try and estimate. Okay, so there's two. I put in two samples. I did it for a reason. The second sample, sample B, which I won't talk much about because I don't have much time, is a sample where in the recurrent class, the Markov process hits a certain number of states and stays among those states. And in the recurrent class, there's no point where the value, where entry in location 2 is greater than entry in location 1. So location 2 is really a bad location in that. And that will affect my ability to estimate things. Okay? The standard one, the more standard one is this one. But I will try and tell you something about this one. The thing to notice here is no matter what you do, if you don't condition on M, 20% of the variance in value is due to this unobservable. Okay? And if you condition on, if you do condition on M, 20% is due to that. If you don't condition on M, which is the typical thing, you don't. That's the reason for the worry in this literature. Fully 60 to 70% is a variance of the unobservable. Okay? So there's a reason you might want to worry about it. Okay? The second thing is you can see in both of these cases that when you do condition on M, okay, both the number of agents in the number of competitors in my location and the number of competitors in the other location are both negative. Okay? But if you don't condition on M, they're positive. And this is the effect that everybody tried to worry about. Okay? The fact that there's market effects and more profitable markets will generate more entry. Okay? And in this case, it all loads on the other location, which should be negative, but is positive when you don't condition on the market effect. Okay? Okay. So it's a discrete choice model, so only affine transformations of the value function are going to be estimable. I can multiply, I can add a constant to everything and multiply through by a constant that's positive and nothing's going to change. Okay? So I can only do relative coefficients, okay? And so the two relative coefficients, the way I'll present them, I could have presented them anyway, is the value of location 2 versus the increment in value or the decrement in value as people enter my location, and the decrement in value, decrement in value is people other location relative to the decrement in value when they enter my location. So I only have two parameters. I could have done it with M, but I want to do I want to also consider the case where M isn't observed. Okay, so that I want to, which is the case that this literature started with. Okay, so there's two ways of doing this. One is the structural model. Okay, so it's going to end up worrying about multiple equilibria. Okay, there are multiple equilibria, which rules out MLE. So in IO, multiple equilibria means if I see the set of unobservables, the set of observables, and the theta, I can't map them into a decision because there's multiple decisions. There's multiple equilibria. So I can't form a likelihood. Okay? So that was one of the decisions, that was one of the problems that faced this literature. And the other problem that faced this literature was the cost shocks were correlated with NL and N minus L. Okay? But this literature ignored this error in the entry value entirely. It just ignored it because it was a structural model and not a reduced form model. You shouldn't get me wrong. I'm all pro structural models, but there's times when you want to be careful. Okay? So I'm going to consider that model. I'm going to consider the reduced form construction, which implies an error in entry values for each LS. Okay, so it's going to allow for this error. So there's three estimators I'm going to show you, and then I'm going to go on to the second example, I hope. The first estimator is really an ingenious set of papers by Elie Tamer and his co-authors. Okay, what they do is they use the necessary conditions. So Nash equilibria will have necessary conditions, which will be true at all equilibria. Okay? So those, they're like first order conditions, but they're discrete, okay, in this case, because it's entry model. Those equilibria generate moment inequalities, not equalities. Okay? And Ellie and his co-authors showed how to use those to estimate parameters, or at least to get set estimators of parameters. Okay? I call there, in a paper I wrote, I call this the generalized discrete choice model. By the way, the problem of multiple equilibria showed up in labor economics a lot, many times before. Heckman used to call it the coherence problem. And we now call it, so it's not new to I/O. So this estimate, it allows for multiplicity and endogeneity, but treats the value function as structural. That is, there's no error in the value function. Okay? And then I'm going to go to estimates of the reduced form function, and I'm going to get you I'm going to start with nonparametric and then parametric. Okay? So the nonparametric bounds, the entry value in our model will just be the 1 minus the distribution of this composite cost error evaluated minus XLS theta plus nu LS. The nu is inside, because it's part of the value. And so this is a question of the cost greater than the value or not. Okay? So I'm just going to call that F bar LS theta, okay, just for shorthand. So what the model delivers is it says, if I order the observations on L and S by the probability of entry, or by the fraction entering, it says that, and K, we start from the lowest, so 1 is the highest number of entrants. So if F bar K is greater than F bar K plus 1, xk plus theta plus nu k must be greater than xk plus theta, 1 theta plus nu k plus 1, because it's just a probability distribution, okay, and we're evaluating it at different places. Okay? So that plus the fact that the nu's are orthogonal to the x's gives you one set of inequalities. You can work through it, but you just order them, and then you multiply the order by the sum of the x's until that point. Okay? And it will work out that that gives the sum of that is just sigma nu k xk, which is the definition of orthogonality. Okay? So that gives you one set of moment inequalities, but it's not very much, right? If I have 5 variables, I want to bind them on both sides, so I need 10 inequalities at least, maybe more. Okay? So this is going to end up being unbounded, and that shouldn't be surprising to those of you who know the discrete choice literature. Rosa Matzkin has several papers on point identification. You can't get that either, so it should not be terribly surprising. So if you're going to go nonparametric, you have to add more information, more structure. Okay? And so one nonparametric possibility is to assume that at a given state, okay, the differences between the nu LS, the unobserved part of the value function, okay, there's a state-specific component and a deviation from the state-specific component. That's without loss of generality. But now I'm going to assume that the deviation of the state-specific component has the same distribution for different L at a given S. Okay? But it's totally free across S. So we can be in environments where there's more uncertainty and environments where there's less uncertainty. That's fine. Okay? It's just that at a given environment, the two agents draw from the same distribution of costs. Okay, so now you have the condition that the difference in if F is greater than L prime, if FL is greater than FL prime, if there's more entry at L than entry at L prime, at least in expectation, GLS has to be greater than GL at prime. This reduced form function has to be greater at LS than it is at L prime S. And that's got to be true if I interact it with any positive number, XS. It's got to be true, so you multiply it by a positive number, it's still true. Okay? And that gives me a set of inequalities, okay, which I can use to form bounds on theta naught. The important part of this one is by taking the difference in the G's, what I do is uh-oh. Somebody want to tell me what to do? I know how to do this on my computer. You know how to do it? Sorry. Oh, that's right. Could have done that. It's not that confusing. Okay, thank you. By taking the difference in the L's, I take out the market effect. So I take out the effect that's bothering me about getting the simultaneity issue. Okay? So I control for it because it's the same for both of them. That's the way the model's written. Okay. So that's two estimators. So the other estimator you could do is you could just make a distributional assumption on the parametric point estimates. Okay? And there's two ways you could do this. You could not allow for a market, you could allow for a, not allow for omitted market-specific effect, or allow for omitted market-specific effect. Okay? This estimator is really easy. Okay? If I have the F bars, okay, all I do is take the inverse of F bar. PLS is the actual observed entry rate for location L at state S. I just take the inverse of it, okay, and that gives me a function. So the inverse, because you have to renormalize with the, if it was normal, for example, you'd have to renormalize with the normal mean and the normal variance, okay? You would get something which is a function of theta, okay? And once I do that, once I have the YLS like that, that function, by the way, I still get my normalized coefficients back. They'll give me exactly the same normalized coefficients, okay? So if that's what I'm after, I'm in business, okay? But then this function is very easy to estimate because lambda theta is just x prime x, x prime inverse x prime y, like OLS. And the only thing is, first you have to take this transpose. So you take the normal inverse or you take the exponential inverse first. Okay? And similarly, you can do this with omitted variables, and you would do it just like last time. You would say VLS equals VS plus a deviation, and then take the difference in the y's. So y1 would be the inverse of P location 1s, and y2 would be the inverse of P location 2s. And this is just like taking the within estimator. Okay? So it's these are very easy things to do. Both parametric estimators are trivially easy to compute. The GDC estimator is not. It's pretty hard to program. I never went through all the details. It's a pretty ingenious estimator, actually. It's hard to program and it's hard to compute. And finding confidence intervals for any of the inequality estimators can be computationally challenging. There are several papers on this, including one by me. So, okay, so here's the estimates. I think it's hard for you to tell what's going on. So let me give you a picture of the estimates first, which will show you exactly what's going on. Control F, does that work? Can you see that? I guess you can see it. Okay, so this is, I'm showing you one picture. I probably can't go through all of them. This is a reduced form when n is not observed, okay? And this is a reduced form when n is observed, okay? And it's a reduced form coefficients when n is observed that I'm after, okay? Though in both of the, okay, and both of the, you can see that both of the estimators. So here you have the GDC estimator. This is the Tamer estimator when you use a log normal for the distribution of the error. And here you have the GDC estimator when you use the exponential as a distribution for the error. And here you have the inverse estimator when you use the exponential for the error. And here you have the inverse estimator when you use the log normal for the error. And these are the nonparametric bounds. So unfortunately, in this case, the nonparametric bounds weren't very tight. Okay, so all these things, and you can see that all of the estimates are within the all the estimates, but the GDC estimates are in the nonparametric bounds. The first thing you should realize is the GDC estimators really do take care a little bit of the endogeneity of M, because they aren't up here; they're way down here. Okay. The second thing is that the bad thing about the GDC estimators, so is that they depend a lot on the actual distribution of the error term that you use. And that's going to be characteristic of discrete choice models, because what you're doing is you're saying, I'm going to enter if my cost draw was in some tail. Is that clear? And tails of distribution vary with distributions very much. Okay? The inverse estimator, it does require the distribution function to do the inverse. But after that, it's just OLS. It's just based on central tendencies. Okay? OLS is just based on the central tendency of the various estimators. Okay, so they actually all do pretty well. The problem is that it is true that GDC seems to be going after the right parameters, okay, but it's very dependent on the functional form for the error distribution. And that's something we really don't know very much about. Okay, so I'm going to now move on to the second example quickly. Talk. Okay. I think I told you all this. Okay. The second example is taken from work. This is actually an empirical example, and it's taken from work by Kate Ho and myself. So this is the response of hospital choice to price when doctors are incentivized to minimize costs. So in the United States, probably most people know this, health insurance is privatized. Okay. At least health insurance beyond Medicare and Medicaid, beyond for the old people and the indigent, is privatized. What happens is there's an HMO, a health maintenance organization, who goes in contracts with groups of doctors, okay, and groups of hospitals, charges a premium to the patient. Patients choose out where they want to go, and then they can choose doctors and hospitals from the doctors and hospitals that the plan is contracted with. Is that clear? That's what's going on. There's the Affordable Care Act. The Patient Affordable Care Act in the United States now is thinking of using capitation to changing the structure of this. This is Obamacare, if you like. Changing the structure of this and making these accountable care organizations. And the accountable care organization is going to be a group of doctors and a group of, sometimes with a hospital, sometimes without a hospital. And they're going to be partially incentivized by capitation. So what's capitation? Capitation is we know how many people are in your plan, okay? We know their ages and something about their proclivities for illness, and we're going to give you a fixed rate at the very beginning, okay? And that's what you get for this patient, and you have to take care of this patient. Okay, so there are quality things and there's a lot of riders on this, okay, as you can well imagine. Okay, but that's what's going on. It works out that in California for the last 10, 15 years, this has been going on. There's been big groups of doctors who have acted like this, and I will show you in a second. And the different doctors and the different HMOs provide different amounts of capitation to the doctors. Okay, so some Pacific Care works out as 97% capitated, and Blue Shield is 33% capitated. So you might want to look at these data and see, is there any relationship between capitation and where the doctor sends the patient? Okay? You also might want to look, is there any relationship between capitation and the quality of care the patient gets? So we're doing all of that, but I'm only going to show you the pricing things. Okay? So the problem with going directly to discrete choice for this, which was the first thing we did, of course, this is when I started thinking about reduced forms. Again, we don't really know the model of hospital choice here. Okay, there is some arrangement between the doctor and the patient. The patient, by the way, we're going to do women who are going to give childbirth. We're actually starting on cancer now, but this is going to be women who are giving childbirth. Women typically choose a doctor knowing the hospital in mind, at least in the United States. Okay, so there's a complicated choicing. Then the doctor is often affiliated with 2 or 3 hospitals and can direct them to one of those 2 or 3 hospitals. And we'll direct them to different hospitals if it's a risky birth and not a risky birth. They'll do different hospitals. So, okay, so the problem with discrete choice is you want to condition, when you do hospital choice, you want to condition on hospital diagnosis-specific interactions. Okay, so you're going to send somebody who has diabetes or a tumor to a different hospital, okay, than a woman who's 20 years old and nothing's wrong with her, and okay, she doesn't want to go to the other hospital. It's farther away. It's more costly. Okay, so every different diagnosis, there's a different ranking of hospitals. Okay, so in our data, there were 106 diagnoses that the Columbia Presbyterian doctors came up with. Okay, that said these are the relevant diagnoses. Okay, so that's one problem. 106 diagnoses at 40 hospitals. There's going to be 200 hospitals, but there's only 40 in the biggest market. So 100 diagnoses in 40 hospitals is 4,000 coefficients. Nobody's ever going to estimate 4,000 coefficients in a discrete choice model. Okay, it's not in the cards. Okay, so that's one problem. Okay, the other problem is this same problem that I harped back to at the beginning. The hospital prices are not known. It is true, by the way, there's been surveys of the doctors. So they've been informed approximately what the prices are at different hospitals, okay? So the best the doctor knows is the expected price when the patient is sent to the hospital. The doctor doesn't know what procedures will be done on the agent, what protocol. He knows that the agent's going in with this particular diagnosis. Okay? And the actual price will depend on all the procedures and the price of the hospital, and the doctor doesn't know them. So he's really basing it on an expected price. Okay? And there are plan-specific discounts. So this is where IO gets difficult. So what's happening in this, it's a multilateral bargaining situation between the HMOs and the hospitals. There's a small number of agents on each side. Is that clear? What's happening is there's a cost of the services at the hospital, and there's the premiums made by the HMO, and there's a pie to split. And the contracts between the HMO and the hospital essentially split this pie. Okay? And what happens is there's prices, which are DRGs for diagnosis research groups, which are set by Medicare and Medicaid. Okay? And what they negotiate on, not totally, it's much more complicated than this, but the major thing they negotiate on is the discount that goes to the HMO on those prices. Okay? And it's not a minor discount. So what we know is only the average discount in a hospital, not to which HMO. Okay? And the average discount is 65%. Okay? So we built a model for the discounts because we have the average discounts in the hospital, but undoubtedly that model has an error in it. So there's measurement error in our discount variable, so in our price model. So what price variable do we use? We look at each hospital and each of these 106 diagnoses, and we take the average price for a given diagnosis at each hospital. Okay, so you come in with a diagnosis, and then there are procedures done to you, and we see the cost of those procedures, at least the DRG costs. Okay? And we take the average of those, and then we multiply it by our predicted discount. So there's going to be two problems, okay, with that. One is, for small diagnosis in a hospital, the average is not going to be exactly equal to the expectation. And two, we're going to have a discount. There's a predicted discount. We're undoubtedly doing that not quite correctly, and there's going to be an error in that. Okay. Okay, so now here's how, I'm going to look for this reduced form, and I'm going to see, does price matter? In particular, does price interacted with capitation matter? Let me just say, there's only been one study that put pricing in hospital choice functions, because everybody said, the patient doesn't pay the price. Nothing matters, okay? And it used just one price for everything done at the hospital, just this one index for the hospital, okay? Okay, so GIH is my reduced form model for what this combination of agent, insurer, doctor chooses, okay? And I'm going to assume it's additively separable in price, perhaps interacted with capitation rates. These planned diagnosis, hospital-specific qualities, all these 40,000 dummy variables, okay? And patient convenience factors. So undoubtedly, in this literature, the most important one is the distance to the hospital. It comes out of every study, okay? Okay, so again, I'm going to start with what you would do standardly. You would think you're estimating a structural model, and you would just do a discrete choice multinomial logit, which is, by the way, what's done in this literature. And we added all the interactions the literature has ever done. We've done a fixed effect for each hospital and interactions between hospital rough diagnosis and hospital effects. Okay? So there's going to be two problems with this. We're not going to fully control for the quality diagnosis interactions because we're going to have 150 dummy variables instead of 4,000. Okay? And our price variable has both expectational error and modeling error. Okay? So here's what happens. This is standard multinomial discrete choice. Here's what happens. If you put all the patients in, and you just do this regression with 194 coefficients for the hospital fixed effects and these 15 interaction terms, you get a positive coefficient, and it's significant. Okay? If then I just say, OK, let's take the half the sample that's least sick. These are women who are under the age of 35, okay, and have no comorbidities. And at 0 Charlson score. This is the score of the index, okay? And you just do them, okay? All of a sudden, you get a negative coefficient. So there's much less variance in the diagnosis among these women, okay? Because they're all reasonably healthy women. There's some variance left. But so the quality interaction shouldn't be as important. And as soon as you take away the quality interactions, okay, you start getting a negative coefficient. Okay? And then if in addition, you say, OK, let's interact the coefficient with capitation rate. Okay? We get a very significant coefficient on the capitation rate. This is just least sick patients. Nobody comes in with no comorbidities. A young woman with no comorbidities. And you can see these are the actual capitation rates in the plan. The first one is Pacific Care, Aetna, HealthNet, Cigna, Blue Shield, and Blue Cross. And so it goes from 0.97 in Pacific Care to 0.38. And the actual estimated coefficients when we do each plan separately go down with the capitation rate pretty strongly. So we did, this is a different regression than this. This one just puts in capitation rate. This one puts in interactions for each plan. Okay? Still, you might be really quite worried about the magnitude of these coefficients, right? Because we already saw that if we take a little bit of account of these hospital quality diagnosis interactions, we change the sign, okay? And we know, in addition to that, we haven't taken care of all of them, we know in addition to that, there's real problems with the price variable, okay? So I'm going to look at a different estimator and compare it, because I'm interested, actually, the health system is interested in exactly what those price coefficients are and how they're related to capitation. They're also interested in the quality terms, which we're also working on, okay? So I'm going to say, I'm going to take two patients in this. So remember, my evaluation function is this function of price, this function of hospital quality diagnosis, and this function of distance, just added. Okay. So I'm going to assume that a patient who goes to hospital H, okay, that patient evaluated at hospital H, the value function for that patient was greater for hospital H than it was for H prime. Okay? That says that the true parameters, or the true reduced form parameters, when I condition on X, okay, that difference has expectation, which is positive. Okay? Now I'm going to look for a second patient in the same plan who has exactly the same diagnosis at another hospital. Okay? In particular, at hospital H prime. Is that clear? So I'm going to say for that patient, okay, that patient likes hospital H prime more than hospital H. So his inequality is this, or her inequality is this. It's got to be positive. But if I take the inequality from the patient who went to hospital H and H prime, and I add it to the inequality of H prime given H, both of them should be expected positive, so the sum is positive, but it differences out the difference in quality in the quality diagnosis interactions. They had both the same diagnosis. Is that clear? I picked the guys with the same diagnosis. One was in hospital H and preferred it to H prime. One was in hospital H prime and preferred it to H. I sum the two, it differences out. And all that's left for me are the price and the distance terms, or the convenience factors. Okay? Moreover, the price has an error, but now I'm just going to average over those patients. And that should average out the error. Okay? I can average out over all the diagnosis now. Okay? As long as I just take two patients who are in the same diagnosis at different hospitals. So I average out all the errors. And I can interact, see, this is supposed to be positive. I can interact it with any positive function and still get another moment inequality. Okay? So what we use is distance to the hospital as the other positive function. So here's the answers. I never put up too much. I'm going to be just in time. Blue Shield, out of the 6 plans that we're in, Blue Shield is the only for-profit plan. So it has other considerations. And it was the only one, I never wrote it down here, but it actually had a coefficient we couldn't tell whether it was positive or negative. It was confidence intervals on both sides. These are, by the way, estimated by moment inequalities, and the confidence intervals are by these confidence intervals in Pakes, Porter, Ho, and Ishii. So you can see the confidence. So it's a moment inequality, right? So you get set estimators. So what I'm giving you, because it's inequality, if it's satisfied by one parameter, it's going to be satisfied typically by more than one parameter. So I'm going to give you bounds on the parameter. In fact, what I'm going to give you is confidence intervals for the whole set, okay, the whole interval. Okay. So Pacific Care, you can see as we go down, they're all negative, okay? And they're more strongly negative, except the only one out of line here, the more strongly negative for the more capitated plans, okay? And by a lot. So I should note, there's a problem here. There's still, all the econometrics hasn't been taken care of, because I've assumed in doing this, and I should have told you this, the estimators assume the hospital quality diagnosis plan effects, these 44,000 interaction terms, 4,000 actually times 6 for 6 plans, 24,000 are the only source of unobserved differences. And I can fix this now, but I haven't done it yet, okay? I can allow also for an epsilon. Okay, So now you want to say, well, let's look at the elasticity of distance for price. Let's keep utility constant. How much distance would I have to get for a given increase in price, or how much price should I have to get for a given mile distance increase? So that you see in the logits, the estimates were 0.33 for Pacific Care, which had the highest capitation rate. Cigna, which was in the middle, was 0.10, and Blue Cross, which was at the bottom, actually got negative, the wrong sign. Okay? If you do it this way, you get elasticities which are a factor of 34. That's a lot. Okay, that will change all the implications. Okay. So thinking through the argument, the reason for this, that I'm doing this, is thinking through what you're doing when you do the reduced form. Okay, is going to be useful. In this case, it lead to much higher effects than from logit analysis, and an effect which varied a great deal with capitation rates. So that's my two examples. Okay, I want to conclude by saying my gut reaction is for reduced forms to be used, to be useful, they should have an interpretation. One obvious interpretation is as a reduced form predictor of agents' evaluations. Okay, and if once you start thinking about that way, there are econometric issues that will be specific to your problem. You have to think through your problem, what's going into the reduced form, and where the problems are that you want to analyze. But you'll have to pay attention to what this expectation is, conditional, and what you're trying to get, what you're trying to learn. Okay, it's not just freehand reduced form. Okay, thank you.
Burning question, or any question, burning or
not
so fiery, that would be fine. That's good. Well, there you are. So I did have one, of course, but I'm going to raise one. So this weak rationality, it seems. How do you? So this idea really has been around, I think, in dynamic models of the more linear kind for a long time, where you condition on, by conditioning, you recover something about kind of partially identify the model. It's almost like it's not really reduced form; it's just getting at part of the structure here. So I guess the idea here you've got is you kind of invert difference. Then you look at the moment inequalities on that, and from that you recover.
Right, but there is a difference. Let me just say, it's not structural. So if you go back to the entry example, okay, which I don't have up, but you'll remember.
Tell us.
Yeah. So in order to get the entry example to get into the reduced form, I had to project the costs out against x.
Yeah.
The behavioral parameters that if I was really going to do policy analysis and change the c, okay, I would need something different. It's just all it is it's the best predictor of the value given what I'm putting into the thing. What I'm putting into the thing may not be all the right things. Okay, it still gives you structure, but it doesn't give you the behavioral interpretation.
Okay, so this is a good thing to carry on the discussion with. So let's thank Ariel again for a great talk. Thank you. Yeah, I think they will.